Modules and Homological Algebra, Lecture 19, Complexes and Homology. We start from the definition of a complex of abelian groups. Let AI be a collection of abelian groups which are indexed by an integer I. For any integer I, let di be a group homomorphism from AI to AI plus 1. Definition: the following construct is called a sequence of abelian groups. So we simply write our abelian groups AI minus 1, AI plus 1, and so on in both directions, and we connect them by our homomorphisms. Di minus 1, which goes from AI minus 1 to AI, Di, which goes from AI to AI plus 1, and so on in both directions. So this is a sequence of abelian groups, and here we denote the sequence by the pair A subbullet, D subbullet, and we usually say that D is a differential. So this is why it's usually denoted by the letter D or some versions of this letter. Next definition: a sequence A bullet, D bullet of abelian groups is called a complex of abelian groups, provided that the square of the differential is 0. Which means that if we compose di after di minus 1, we get 0 for all integers I. Equivalently, A bullet is a complex if and only if the image of di minus 1 belongs to the kernel of di for any integer I. Here is an example of a complex. So we take all our abelian groups to be equal to z sub 4. So this is the cyclic abelian group of order 4 with respect to addition. And as our differential, we take the multiplication by 2. So each di is equal to the homomorphism from z4 to z4, which is given by multiplication by 2. So now the square of the differential is then multiplication by 2 times 2, which is 4. And of course, multiplication by 4 is the zero homomorphism from z4 to z4. Therefore, this is a complex of abelian groups. This defines complexes and sequences of abelian groups, and similarly, one defines complexes and sequences of modules over an arbitrary ring R. Next, let us define homomorphisms of complexes. Let A bullet and B bullet be two complexes. So let the differential in A be denoted by D, and the differential in B be denoted by delta. Definition: a homomorphism from the complex A bullet to the complex B bullet is a collection F bullet of homomorphisms. So for each integer I, we have a homomorphism Fi from AI to Bi, such that for each integer I, the composition of Fi after D sub I minus 1 equals the composition of delta sub I minus 1 after F sub I minus 1. In other words, the following diagram commutes. So we draw in the first line our complex AD. So we have AI minus 1, and then Di minus 1 goes to AI, and then Di goes to AI plus 1, and so on. And in the second line, we have our complex B. So we have dot, 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 and then a morphism into Bi minus 1, then delta I minus 1 goes to Bi, then delta I goes to Bi plus 1, and so on. And vertically, we have Fi minus 1, which goes from Ai minus 1 to Bi minus 1, Fi, which goes from Ai to Bi, and so on. And this diagram should commute for F to be a homomorphism from a complex A bullet to a complex B bullet. For example, example 1, the collection of identity morphisms defines the identity homomorphism ID bullet from any complex A bullet to itself. Example 2, the collection of zero morphisms defines a homomorphism 0 bullet from any A bullet to any B bullet. And in both cases, the fact that the corresponding diagram commutes is obvious. Next, we can define the category of complexes. Given a morphism F bullet from a complex A bullet to a complex B bullet, and a morphism G bullet from the complex B bullet to some other complex C bullet, we can compose G after F by composing Gi after Fi for each integer I. And this gives us a morphism from A bullet to C bullet. And this composition is obviously associative because it reduces to composition of maps, which is an associative operation. And the identity morphisms, of course, serve as the identities with respect to this composition. This implies that we can define the category of complexes of abelian groups, denoted com of ab. The objects of this category are complexes of abelian groups. The morphisms are homomorphisms of complexes. Composition is composition of morphisms. And identities are the identity morphisms. And similarly, we can define the category of complexes of R modules for any ring R. The category of all complexes has various classical subcategories. A complex A bullet is called bounded on the right, provided that AI is 0 for all I big enough. It is called bounded on the left, provided that AI is 0 for all I small enough. And it is called bounded, provided that it is bounded both on the right and on the left. And now we can define the following full subcategories of the category of complexes of abelian groups. Hom upper minus up. So this is a category which consists of all complexes bounded on the right. Hom upper plus up. So this consists of all complexes bounded on the left. And com upper b up, which consists of all bounded complexes. And we can define similar categories of complexes over the category of R modules for any ring R. So we have com upper minus of R mod, com upper plus of R mod, and com upper b of R mod. Next, let us define the notion of homology. Let A bullet and D bullet be a complex. Then, as we already mentioned, the image of di minus 1 belongs to the kernel of di for all I. Definition: for a fixed integer I, the I's homology of our complex is defined as the abelian group given as the quotient of the kernel of di by the image of di minus 1. And the usual notation is H sub I of A bullet. For example, if you consider the following complex, so it has the following abelian groups, so all zeros, and then z, z sub 10, z sub 10, 0. And the homomorphism from z to z sub 10 is multiplication by 4, and the homomorphism from z sub 10 to z sub 10 is multiplication by 5. And here, the original z is in position 0. This is a complex because 4 times 5 is 20, and this is divisible by 10. So the composition of these two multiplications is the 0 map. And here is the homology of this complex. In position 0, and this is the position of z, the elements which go to 0 in z10 are exactly the integers divisible by 5. So the homology here consists of all integers divisible by 5. This is a kernel, and the image of the 0 map is 0. So the homology is the group 5z, which is a subgroup of z, and it is isomorphic to z. In position 2, we have here the 0 map, so the kernel is z sub 10, and the image of the homomorphism of multiplication by 5 is 5z sub 10, and the corresponding quotient is, of course, z sub 10 divided by 5 times z sub 10. This is exactly z sub 5. So here, the homology at position 2 is the abelian group z sub 5. So, and the claim is that at all other positions, the homology is 0. So this is clear for everything on the left and everything on the right of zeros. So let us explain why the homology at position 1 is 0. So the kernel of the map of multiplication by 5 is, of course, the subgroup generated by 2. And when we have the map from z to z sub 10, which is given by multiplication by 4, its image is exactly the same subgroup. So if you take the element 3 times 4 is 12, modulo 10 is 2, which means that the generator 2 of our kernel belongs to the image. So the kernel is equal to the image, which means that the homology at this position 1 is 0. Next, let us describe how homomorphisms of complexes related to homology. Proposition: let F be a morphism from a complex A to a complex B. Then each Fi, where I is an integer, induces a homomorphism from the i's homology of A to the i's homology of B. Proof: what we need to prove is that Fi maps the kernel of the differential in A to the kernel of the corresponding differential in B, and also that it maps the image of the differential in A to the image of the corresponding differential in B. To prove the first claim, let V be an element in AI and assume that it's in the kernel of Di, so Di of V is 0. Then, if we apply to Di of V, which is 0, the homomorphism Fi plus 1, we will get 0. But Fi plus 1 after Di is equal to delta I after Fi of V. And this means that 0 is equal to delta I applied to Fi of V. In other words, Fi of V belongs to the kernel of delta I. This proves the first claim. For the second claim, let V be an element in AI, which has the form di minus 1 applied to W for some element W in AI minus 1. Then, here is a typo, there should be no 0 is equal. So what we can say is that if we apply Fi to di minus 1 of W, this is equal to delta I minus 1 applied to Fi minus 1 of W, and hence Fi of V belongs to the image of delta I minus 1. Because here we have Fi of V on the left-hand side, and we can rewrite it in the form delta I minus 1 applied to something. This proves the second claim. Now let us talk about exact complexes. Definition: a complex A is called exact, provided that all homology groups in A are 0. This means, in particular, that the kernel of Di is equal to the image of Di minus 1 for all integers I. Here's an example. So this is our first example of a complex. So all positions contain the cyclic abelian group of order 4, Z4, and all differentials are given by multiplication by 2. So the image of any differential consists of the subgroup of Z4, which is generated by 2. And this subgroup coincides with the kernel of the differential, which is multiplication by 2. So at each position, the image is equal to the kernel, so this complex is exact. Example 2. Here is an example of a complex which is not exact. So this was our second example of the complex, where we had 3 non-zero positions. So the first one containing z, and then z10, and then z10. The first differential is multiplication by 4, and the second multiplication by 5. Here we saw that we have non-zero homology at position 0, which was 5z, and also non-zero homology at position 2, which was z sub 5. So this complex is by definition not exact. Additional terminology: if the homology at position I in the complex A is equal to 0, one usually says that A is exact in this position. Now let us discuss short exact sequences. Definition: a short exact sequence, which is usually abbreviated by SES, is a complex of the following form. So we only have 3 consecutive potentially non-zero positions, and the rest is 0. So we have 0 goes to x, and then morphism f to y, then morphism g to z, and then it goes to 0. A short exact sequence is a complex with 3 non-zero or potentially non-zero positions. Note that this is a complex if and only if the image of f belongs to the kernel of G. So the differential composition of G after f should be 0. And this complex is exact if and only if f is injective. So this is exactly the claim that this complex is exact at the position of x. Then G should be surjective, so this guarantees exactness in the position of z. And finally, the image of f should coincide with the kernel of G. This provides exactness in the position of y. So here's an example of a short exact sequence, a concrete one. So we have z, which is embedded into z using multiplication by 2. The second z is projected onto z2 using the canonical projection, and that's it. This is a short exact sequence of abelian groups. Now we can discuss functors induced from abelian groups to complexes, or more generally from modules to complexes. Let R and S be 2 rings. Let F be a functor from the category of R modules to the category of S modules. Then application of F pointwise gives rise to a functor from the category of complexes of R modules to the category of complexes of S modules. It sends a complex A bullet, D bullet to the following complex. So our new abelian groups are f of a minus 1, f of ai, f of ai plus 1, and so on. And our new differential is f of di minus 1, f of di, f of di plus 1, and so on. Furthermore, a morphism f from A to B is sent by our functor f to the following diagram. So we have the complex f of A and the complex f of B, and now we apply our functor capital F to each little f sub I minus 1, little f sub I, little f sub I plus 1. So these are morphisms. When we apply capital F, we will get that capital F of little f sub I is a morphism from capital F applied to AI to capital F applied to BI, and so on. So we get such a commutative diagram. This implies that our functor f from R mod to S mod gives rise to a functor from the category of complexes of R mod to the category of complexes of S mod. Now we can define the notion of an exact functor. Let R and S be 2 rings. Let f be a functor from R mod to S mod. We say that f is exact provided that the induced functor from the category of complexes over R mod to the category of complexes over S mod sends exact complexes to exact complexes. Example 1, the identity functor from R mod to R mod is obviously exact. Example 2, the zero functor from R mod to S mod is obviously exact. Example 3, the endofunctor of abelian groups given by taking homomorphisms as abelian groups from the abelian group Z sub 2 to something, we claim that this functor is not exact. Indeed. Let us start from the following complex of abelian groups. So we have the short exact sequence, which we already had before. So we start from Z, we use multiplication by 2 to embed it into Z, and then we use the canonical projection to project the outcome on Z2. So the composition here is multiplication by 2, which is the trivial morphism from Z to Z sub 2. So this is a short exact sequence. If we apply hom from Z sub 2 to it, Then we will have the following sequence. So there are no homes from z sub 2 to z, so it's only the 0 home. Similarly here, only the 0 home, but there are 2 homes from z sub 2 to itself. So we will have z sub 2 here at this position. And so we have now a complex where we have everywhere 0 except for one position. This is not exact, because the homology in this position is z sub 2. So which means that our functor sends an exact sequence to a non-exact sequence. So it is not an exact functor. Now we want to give a characterization for exact functors of some particular type. And we will relate this to the notion of projective objects, which we discussed in a previous lecture. So let R be a ring and X an R module. Recall that X is projective provided that for any surjective morphism pi from some module M to some module N, and I'm working in the category of finitely generated R modules here, any morphism from X to N factors via pi. Theorem: the functor hom sub R from X to blank, and this is a functor from R mod to abelian groups. So this functor is exact if and only if X is projective. So we have to prove 2 claims here. We have to prove implications in both directions. First, let us assume that our functor homin from X is exact. Consider the following short exact sequence. So in the definition of the projective object, we have any epimorphism from M to N, and we embed this epimorphism into a short exact sequence where we start from the kernel of this projection pi, we embed it into N, and then we use our projection pi onto N. This is a short exact sequence. Since the functor of homin from X is exact, applied to the sequence, it gives us the induced exact sequence. So we have that homs from X to the kernel of pi, they embed into homs from X to M, and then this projects onto homs from X to N. This means exactly that if we take any hom from X to N, it is the image under postcomposition with pi of some hom from X to N. And this gives exactly the definition that X is a projective module. This gives us one implication. Let us prove the second one. Assume that X is a projective module. Consider an exact sequence of R modules, which is a complex consisting of the R modules ni-1, and I plus 1, and so on, and module homomorphisms fi-1, fi, and so on. We need to prove that the induced sequence, which is obtained from this one by applying the functor homin from X, is exact at each position. At position I, we have the following part of that sequence. So we have hom from X to ni-1, postcomposing with f sub i-1, we go to hom from X to ni, and postcomposing with fi, we go to hom from X to ni plus 1. Now let G be an element here, which is sent to 0 under postcomposition with fi. So this means that G is a morphism from X to ni, which gets sent to 0 when postcomposing with fi. But this means that the image of G belongs to the kernel of fi. Since the original sequence was assumed to be exact, the kernel of fi equals the image of fi-1. So our map G really is a homomorphism from X to the image of fi-1. And fi-1 induces a surjection from n-1 to this image, to the image of fi-1. Since we assume that X is projective, we can factor G through fi-1, because it is a surjection onto the image, and G maps X onto that image. In other words, G is in the image of postcomposition with Fi minus 1. And this is exactly the exactness of our induced complex at this position. So we are done and the proof is complete. Now let us finish this lecture with some problems and questions. Question 1. Check with all details that the composition of two morphisms between complexes is a morphism between complexes. Question 2. Prove that a complex of the form 0 goes to x, and x goes via f to y, and y goes to 0, that this complex is exact if and only if f is an isomorphism. Question 3. Define the direct sum of complexes and show that it has properties similar to the ones enjoyed by the direct sum of modules. Question 4. Determine all homologies for the following complex. So we have 0 goes to z, and then y multiplication with 6 it goes to z, y multiplication with 15 it goes to z sub 9, and y multiplication with 3 it goes to z sub 9. And then this goes to 0. And question 5, determine whether the endofunctor of the category of abelian groups given by tensoring with the abelian group Z sub 3 is exact or not. Thank you very much and see you next time.